All right, welcome to lesson number 3 on exponential and logarithmic functions, and we're going to start looking at exponential functions today. So the first one we're going to check out is exponential growth, and then we're going to take a look at exponential decay. Now, some of this might be familiar from when we examined it when we talked about sequences and series. So it may be a little bit of a review. So in this first example, a medical research scientist discovers a new bacteria culture which could help strengthen a person's immune system. To find the growth rate, she isolated 5 of the cells of the culture and observed the following growth pattern. After 1 hour, there were 10 cells. 2 hours, there were 20. 3 hours, there were 40. So we're going to be given a formula when t is going to represent the time in hours, and n of t represents the number of cells after t hours. And so the formula for n of t as a function of t can be written in this form. N of t is equal to ab to the power of t, where a and b are constants, and a and b both have to be greater than 0. So what we're looking to do is determine what a and b actually are. Okay, so let's dive into this. Now, if I were to look at my first 5 cells when I had 5 cells, that means that using this formula of n of t is equal to ab to the power of t, n of t in the first scenario will be 5. And if I use ab and for t is equal to 0, I'm going to be left with 5 is equal to a times b to the power of 0. And we know that b to the power of 0 is just going to be 1. If I just have 1 there, all I'm left with is a. So I have my first value for a, which is 5. Now let's look at the second scenario. After 1 hour, there are 10 cells. So when time was 1, we have 10 cells. Now let's plug this into our equation where 10 is equal to n of t, and that is equal to a times b to the power of t. Remember, we found that a was actually equal to 5, so you can have 5 to the power of 5 times b to the power of t, which is 1. b to the power of 1 is just b, so 10 is equal to 5b. If we solve for b, we are going to get a value of b is equal to 2. So a is equal to 5, and b is equal to 2. Oh, that sounds like jet, so I'll be right back. All right, so for the part B, all I did was I used the formula and I plugged in my time of t into the equation. So when n of t is equal to ab to the power of t, when time is equal to 8, or t is equal to 8, I substitute all my values of t with 8, and I got 1,280 cells. Now for part C, after 12 hours, there are 20,480 cells. How many hours did it take to have half that amount? So how many hours did it take to have 10,240 cells? Well, if we look at our graph in the top right corner, or not our graph, but our table of values in the top right corner, we'll see that every hour that passes doubles the amount of cells. All right, so we have this representing exponential growth where our number of cells or our culture is going to double. And so if I'm going backwards, that means that in order to get half of this had to be the time interval before 12, which means that since it's doubling every hour, to go backwards to have half the amount would have been at 11 hours. Now the next thing we're going to do is use a graphing calculator to graph our function, and a graph of this type of function will represent the exponential growth. All right, so when we put this in your calculator, it's just gonna, since we're starting at 5, and we'll start at 5, but then if it's increasing exponentially, it's going to look something like this. Okay, let's look at the next example. Now, in this example, we're looking at exponential decay, and I'm just going to go through it quickly. I'll let you go through and do the actual calculations in this part, but if we're decaying exponentially, I just wanted to show you what the graph look like. With the exponential growth, notice that for every time interval, we're doubling. Now, if we're looking at the exponential decay, what's going to happen is if we're starting at a certain value, and in this case, we're starting at 32,768, and so it's looking at the example of Chernobyl, and at the time of the explosion, the atmosphere was contaminated with 32,000 units of radioactive iodine. And then after 1 week, there were 16,000 units, then 8,000, then 4,000, and so it's being halved every time. So use T to represent the time in weeks, and N of T represent the number of units of radioactive iodine after T weeks. And then complete the following equation of the function, which represents the information provided. So N of T is equal to 32,000. That's what we started with. And then we're using what we're doubling, or what we are halving by. And in this case, since it's a half-life we're working with, the time is going to be halved each time. And so our exponential decay is going to look a little bit the opposite. It's going to look like this. And so I'll let you go through and you can solve part B for yourself. All right, so let's look at our next examples here. So when we're looking at exponential functions, an exponential function is a function whose equation is of the form y is equal to a times b to the power of x, where a can't equal 0 and b has to be greater than 0, but can't equal 1. And they're all elements of real numbers. So let's compare the graphs of 2 to the power of x and 1/2 to the power of x. So 2 to the power of x, we know it looks like what we just kind of looked at. And if I compare this to 0.5 to the power of x, it looks like an opposite regression. Okay, so it's going the opposite direction, and it looks like it's just being reflected across the y-axis. So we want to sketch both of these now. And so if we zoom in, you can see where each of them are actually intersecting. So they're both intersecting at 1, the y-axis at 1. And so if I state the values of a and b, well, in this case, a is equal to 1. And if I look at what a and b actually means, a is the coefficient in front of not the coefficient, but it's the constant term in front of the coefficient. The coefficient is the one that is tied to the exponent. So in this case, 2 is my coefficient. And so a, if I look at this, a is equal to 1, and b, that's the one that's tied to the exponent, is equal to 2. So b is my coefficient. And in this case, a is equal to 1, and b is equal to 1/2. And so if we were to draw both of these, they're going to look something like this, and something like this. Right? That should be symmetrical, but hopefully you get the picture there. Now, what I want to do is sketch the graph of the exponential function with the equation of y is equal to 2x, and we'll use the table of values that is on our grid. And so in order to get to that table, first of all, let me only focus on the one graph. So I only want to focus on y is equal to 2 to the power of x. And so if I do that, I get all these values, and we want to start at -3, when x is negative 3, I have 0.125 or 1/8. I'm just going to look at the table of values on my graph here. So we're starting at negative 3. So I have 1/8, 1/4, 1/2, 1, 2, 4, 8, and 16. All right, so all I used were these values that correspond to my domain and my range. Now we're going to do the exact same thing for the other function, y is equal to 1/2 to the power of x. And we're going to go second function table to look at, or second function graph to look at our table of values. And again, we're going to start at negative 3. So at negative 3, I'm at 8, 4, 2, 1, 1/2, 1/4, 1/8, and 1/16. All right, so if you look at what's going on, it's following the opposite. Oh, sorry, you can't even see those. It's following the opposite trend, right? With the exception of our point at 0, which is our y-intercept. Now, you already know what asymptotes are. You were introduced to those a couple units ago and a little bit last semester. What we're looking for here is to complete this following this chart where we're looking for our horizontal asymptotes. And we know that the x-axis is the horizontal asymptote. So if we look at the domains of either of our functions, where y is equal to 2 to the power of x, the domain is x is an element of real numbers. Now if I look at the range of the function of 2 to the power of x, so we actually have a horizontal asymptote, so it's never gonna cross 0. So that means that my domain, and it's gonna go on to infinity, but my domain is always gonna be greater than 0, such that it's an element of real numbers. Which means that since it doesn't cross the x-intercept, there is no x-intercept. And if we look at our graph, the y-intercept is at 1. And the equation of my asymptote, remember that's where we had a horizontal asymptote, that's when y is equal to 0. And for our other graph, it's actually going to be the exact same thing. X is an element of real numbers. Again, y has to be greater than 0, such that y is an element of real numbers. There's no x-intercept because it doesn't cross the horizontal axis. The y-intercept's the same, and the asymptotes are the same. Now, if we look at both of these, complete the function using the words growth or decay, 2x, remember it's going upwards. It has an upward trend, and so that's a growth function. And 1/2 to the power of x is an example of a decay function because it's going down. The values are getting smaller. And next, let's look at this section here. All you need to do is use your graphing calculator to sketch the exponential functions with the equations, right? And so when you type in all your graphing in your graphing calculator, you'll find that all of them are going to have a y-intercept of 0. So they're all going to cross the y-axis at 0. And I'm not going to do this part because all you need to do is type these into your calculator and you're going to get your lines. And just quickly I'll show you what some of them will look like. So if you're looking for y is equal to 3x, you're going to look 3 to the power of x, it's going to look something like that. Y to the power, and this is y is equal to 3 of x. 1/3 x is going to look something like this. All right, so hopefully you kind of get the picture here. And then what we're going to do, we're going to have to do is look at the relationships between all of our lines. So the value of b affects the steepness of the graph as x increases. All right, so complete the following when b is greater than 1. Well, when b was greater than 1, and so you'll look at the two examples with 1/3 and 1/10. But when b is greater than 1, then your curve should be rising. The curve rises more sharply as the value of b increases. When b is greater than 0 but less than 1, your curve should be falling. It should fall more sharply as b decreases. Now, without using a graphing calculator, make a sketch of the graphs of y is equal to 5 to the x and y is equal to 0.2 to the power of x. Right, so without using a graphing calculator, you should be, after doing the first example here, you should be able to kind of visualize what's going to happen. Since this is greater than 1, we're going to have something that's going to curve quite sharply upwards. And since I have 0.2, I have the inverse of this, it's going to go down the other way. So 0.2 is the same thing as 1/5. And then the rest of this, I'm going to let you guys take care of, because you should be able to answer these questions because they're not going to change based on that table that we already did. Okay, so let's look at exploring the value of a in y is equal to a times b to the power of x. Okay, so the first thing we want to do is graph all of these. Consider the following functions with the equations, and they're in the form of y equals a b to the power of x. And yeah, we want to graph these. So 3 to the power of x, 2 times 3 to the power of x. I'm just going to graph them how they're given here. 5 times 3 to the power of x, and 0.5 3 to the power of x. And so all four of them are going to pop up here. This is the first one of 3 to the power of x. It's crossing at 1. The next one is 2 times 3 to the power of x. This one is 5. And the last one is 0.5. Now notice where all the y-intercepts are. They're all where the a value is. So your value of a is going to correspond to your y-intercept. So I was at 0.5, 1, 3, and this, if I zoom out here, you'll see that this last one is at 5. Not the last one, but one of them will be at 5. So 1, 2, 3, 4, 5. So right here, it should go up. There it is. Okay, so this is what we want to graph now. So my first one, where y is equal to 3 of x, since there is no value of a here, we assume that that's 1, in brackets of course, and so that means it's crossing my y-axis at 1. When it was at 2, it's crossing at 2. So this is y is equal to 3 to the power of x. This is y is equal to 2 times 3 to the power of x. 1, 2, 3, 4, 5. This is y is equal to 5 times 3 to the power of x. And my last one, when it's at 0.5, it's going to look something like that. Y is equal to 0.5 3 to the power of x. Now let's fill in this table. My value of a when y is equal to 3x, remember, that's 1. So that's 1. And because we're using this form of the equation, y is equal to ab to the power of x. And so here my value of a is 2, here it's 5, and here it's 0.5. Now looking at my value of b, for all of them, my value of b is 3, right? Now the y-intercept on the graph is going to correspond to my value of a. So that was 1, 2, 5, and 0.5, or 1/2. So what is the effect if we change the graph by changing the value of a? Well, if we change the value of a, we're going to have a vertical stretch. So we're going to move away from the x-axis. Vertical stretch about the x-axis. Now, if f of x is equal to 3 of x, write the following in terms of the function f. And so y in this case would equal f of x, since f of x is equal to 3x. In this case, y is equal to 2 f of x, since again f of x is equal to 3 to the power of x. In this case, y is going to be 5 times f of x. In this last case, 0.5 times f of x, which is 3 to the power of x, y is equal to 0.5 f of x. Now, which transformations are associated with 2, 3, and 4? Well, with 2, the transformation that's associated with 2, with all of these, with 2, 3, and 4, is a vertical stretch. They're all vertical stretches. By a certain factor. By a factor of, well, for 2, let's look at it. If f of x was equal to 3 to the power of x, and my value of a was 1, when I looked at my scenario 2 here, where I multiply it by 2, I increased from 1 to 2. So that means I had a vertical stretch by a factor of 2. If I look at my third scenario, where I went from 1 to 5, that means I stretched by a factor of 5. And then in my fourth scenario, I went from 1 to 0.5, which means I'm stretching by a factor of 0.5. So I'm actually compressing that graph. And now last, what is the effect of the parameter a on the graph of y is equal to a times b to the power of x? Well, that's going to result in a vertical stretch. Vertical stretch about the x-axis. Now say the y-intercept for each of the following graphs of the form y is equal to a times b to the power of x. Well, my y-intercept is going to be a.